Alright. On the test, the first problem was what most people struggled with. So I'll go over some of those for review at the end of the semester. John?
Real quick on the least, the y direction is always the same before and after.
Yes.
It's not alternate for some reason.
The tangential direction is always the same. And so the y direction happens to be the tangential direction. All right, this is number 3 on the homework, which is not on the book, right? So, free body diagram, what do we have? MG, because if this were ice, it would slide without rotating. And this is equal to what? Alpha. Where's our happy point?
The theta at the bottom.
Some of them is about here. So if we take the sum of the moments, which is, what is it, mg r, where is theta? Do you have a theta?
Yeah, it's
R sine theta, what's that equal to? Mass times acceleration times r plus I.
What would I do in this case?
I is whatever they said I.
They said, is that, or no, that's a different one, or not, yeah.
Whatever, if it's a disk, it's 1/2 m squared. I don't know. A hoop?
It's a hoop, yeah.
A hoop, then I equals mass r
But
squared. All the mass is the distance r.
you're looking at it as it's rotating about the center, right?
No, it's not rotating.
It's
Where's the instant center?
Okay, so that changes the. Oh, you.
Some of the moments about the point of contact, and so.
So then you do just parallel axis theorem. Because it's not.
When you do this, it will end up with a parallel axis.
Oh, that's what that is. Okay.
But it's the effective force times the distance.
Oh.
It's this times r is the moment of this mass times acceleration about the ground.
So then how do you get rid of alpha?
A equals r alpha.
And then what is a way to tell which way friction is going with all these different, I mean, I know if you're pushing it, it's sliding, like that, but because there's ones where if you're pulling it,
Basically, if you don't have a moment, and this was ice, this is just going to slide down the hill, and so friction is going the other way
make it roll.
to make it roll.
Okay.
If you have a motor, what happens?
Reverse friction.
Next one.
You never got mass. Your wheel is just going to spin, and so therefore the bottom of the wheel is going to be going like this, and then friction is going to be going the opposite direction. So if you have a moment, then friction goes pushing you in the direction you're going to go. If you don't have a moment, then friction opposes your motion.
Okay, so what about if you have a thing like that, it's on something that's accelerating? And this is like there ends up resting, and this starts accelerating that way. And then so this is
How is it accelerating?
It's on a truck.
On a truck.
There's a roll of something on a truck, and it's at rest, and the truck starts accelerating this way, and this roll is free to move.
Okay.
So which moves? Because the center is going to want to go with the truck, right?
What? No. This is a point of contact.
Oh, yeah, that.
So the question, what problem was this?
Number 6.
Number 6. Right, you have something like this. And you basically are given a truck.
So then I want to roll back, right?
So here's something that's not going to roll. Here we have the truck. What's going to happen? Which way is it sliding? The sliding relative motion is sliding this way, so friction is going to be pushing there.
So I have to mind direction friction, right?
Correct.
And then which way is it going? It's going to roll back?
It's gonna roll forward with the truck.
It's going to roll forward.
Because if you like.
It's going to roll back on the truck, because the truck is going forward. The center of it is going to be moving forward.
The center's moving forward, but it's rolling back.
But it's rolling back inside the truck until it hits the back of the truck.
Okay.
So because friction is pointing this way, the only horizontal force is forward, the net force is going to be moving forward. Now, it's going to roll backwards, so the acceleration will be the same.
The last problem, I was having
Okay,
trouble.
last problem, does it have a?
18.32.
18.32, that.
I was just having trouble figuring out which things to consider and how.
18.32. This is,
Yeah.
yeah.
I think part of my confusion was just the concept that at that point, isn't everything 0? So are you looking at the
What
very
do you mean
instant?
everything's 0?
Because it hits the end of its, like,
Yeah.
the full extended, like the motion and everything.
So,
is 0.
right, we had, whatever, 3, and then this distance is x. So one way we can look at it is, but yeah, at the extreme position, the velocity of the center is 0, right? Because the velocity here is this way. So v equals 0, this is ground. So what, this is going to have kinetic energy, right? Because you're still going to have omega, so you're going to have an I omega squared kinetic energy there. This is also going to be rotating, so you're going to have a 1/2 I omega squared there. And then the spring, right, you're going to have a 1/2 kx squared, or a ks squared for the spring.
Is that, are those two 1/2 IA omega squareds for both the rods, or is that the disc?
Both of the rods. And this one, v is equal to 0, therefore omega d equals 0. Right? And then each of these will also have an mgh CG term for potential energy.
How would you calculate the omegas then for the rod? That's so is hard time with, 'cause is that just relative velocity?
Yeah, the velocity here, what do we have? Where's our instant center? What do we know about the velocity at the end? The velocity here we know because it's attached to here is going to be downwards. So the instant center has to be lying somewhere along this line. What about this point? What do we know about this point? The velocity is horizontal, so therefore the instant center has to lie somewhere on that line. So where does it intersect? Right here. So therefore the velocity at that point is 0. That's how we could have gotten the fact that that velocity is equal to 0. So how do you get the, basically what do you have? You have, each of these since the velocity here is 0, the velocity is here is 0, they're equal lengths. So therefore, they're going to have equal omegas, but they're just going to be in opposite direction. It starts at rest, right?
Right.
So you're going to have your initial potential energy, which is mgh, and you're going to have 2 of those. And that's equal to 1/2 I omega squared 2 plus 1/2 k. It's the height of the center of gravity. H is always the height of the center of gravity. What is the height of the center of gravity? Oh, okay.
Not very good.
Well, this is 45 degrees. So the height of the center of gravity is going to be L over 2.
Would the disk affect that at all? Because it's resisting it falling down. Or no?
It is, but at that instant, its velocity is 0 and its omega is 0. So therefore, it has 0 kinetic energy. This is sort of the philosophy of the floating arm trebuchet. That basically your counterweight at the very bottom stops, so all of the energy goes into swinging of the arms to throw your projectile a lot further. So at this instant, this stops, and so this has no energy, and all of the energy just is purely swinging. But any other point in its life, it will have energy. So this is L over 2 times sine 45. Other questions?
Yeah.
Number 4.
I think you kind of answered it because they're saying that the engine drives only the front wheels and the front wheels.
Okay.
I think that they have a differential on the opposite part and back wheels and the front wheels.
So the front wheels just roll?
Yeah.
Are they significant mass or?
No, it says neglect mass limits.
Yeah. So you have mg.
Doesn't matter.
So I guess
And then it's front wheel drive?
Back one. So there's no friction on the front? No.
Because the friction, all the friction does in the front wheels cause it to roll. And so you assume with wheels it would be higher friction. On the front wheel.
So then our 0.2 term.
So this term goes away. And what are we trying to figure out? Maximum acceleration with, so maximum acceleration, F is equal to mu s times n2. Right, so you have 3 equations, some of the forces y, some of the forces x, and some of the moments. What are we looking for?
They want the time it takes to accelerate to search velocity, so we'll do acceleration.
So once you have the acceleration, then you can go back to chapter 12. Okay? So basically what happens as you accelerate, what does this force want to do? Yeah, this force wants you to tip your car like that, basically, so then the extreme increasing the force on N2. You have front wheel drive. It's the opposite, so you get less traction on front wheel drive. What happens if you get four wheel drive? What's your max acceleration? So you have friction force here, and so it would be friction times N1 plus N2, which is basically mu times mg. So the really expensive sport cars have four-wheel drive. So you get that extra acceleration. All right, other questions? Yeah.
The first 2 years of your entire college.
18.8.
Talk about every class in like I'm gonna talk about the trip I went to, so I just went out and did trips. It's like to fulfill a Christian you see how much they lost? The question is it double spaced?
Can you figure out what the force is at C?
It's at 1.5. Follow the format. I'm assuming it's double spaced. Yeah,
So we have a force P. What's the reaction force going to be? Right? How do we figure that out? Well, that's statics. So some of the moments about we have R, X, R, Y. So we have some of the moments about here is equal to 0. So we get R times 0.5 minus P times 0.75 plus 0.5 equals 0. So we can find a reaction force. Now we have equal and opposite reaction. You have another color? You had blue earlier today? There it is. So now we know R. What else do we have?
You've done one.
Friction. So are we, is it sliding or not sliding? It's not sliding? If it's not sliding, then it's not moving, and that's statics once again. You have mu k is 0.5. So we have mu k times R. So that's our friction force, which is keeping us from falling uncontrollably. What other forces do we have? The red is the opposite direction as the P. Some of the moments. Oh, to get rid of these two unknowns.
Right, so the R.
I changed my direction of health on.
See how close to how we can wait for
Right, we have mg. The reaction forces of the skin. What's that equal to? What's over here? You have the mass and the acceleration. What else is going to happen?
Actual drum break.
By megadot. And what else do we have? We had to distance. I guess if this is R1, R2. Where do we go from here? We want to figure out what? We have initial. We have initial velocity. We know basically we know the initial velocity. We can find the acceleration. How do we go? Where do we go from there? How do we find the acceleration? Some of the moments. Where do we want to take our moments about? Oh, why do we like that point? Get rid of fewer of our unknowns that we don't care about in this problem. So what's that equal to? Is mg times r1 minus uk times whatever r is times I don't know. Now we have two r's. Because the radius r and the reaction r. And r. That's r is it's r2, okay. And that's equal to what? I alpha plus and since this doesn't slip, we get that A equals R1 alpha. So the sum of the moments equals the sum of the effects of the moments. Treating this MA as a force times the distance really gives you a lot of power because then you can take your moments about any point. If we didn't have that, then how would we have to solve the problem? Well, we'd have to have basically break it into the top part and the bottom part, have the tension in the rope. So then you end up with 4 equations and 4 unknowns. No, it just gets messy. All right, that's half the class. Other questions? Okay. So we've checked the homework. I think hopefully, I don't know, we were halfway done. Linear and angular momentum. We had linear momentum, what was that? MV. So what do you think angular momentum is going to be? I omega. So looking at that, and then look at impulse momentum. We can have an angular impulse and a linear impulse. So hopefully you were just listening. All right, what's angular momentum? There's 2 more lectures, and then we're done with getting new content, and then we'll just get, well, we're a half day behind. But then we're basically going to be doing review problems for the rest of the, trying to get us all. All right, so you're 20 people here today, I guess? Hopefully that's me, the right answer. So it's I, G, omega is your angular momentum. If we're rotating about a fixed axis passing through its center of mass, what is its linear momentum? So we're rotating about a center of mass. What is the linear momentum? Choose the best answer. One more person, one more. 3, 2, 1. B is the right answer.
Why?
Why'd you get that?
It's not translated.
It's not translated.
We are rotating about its center of mass. Therefore, the velocity of the center of mass is 0.
Wait, MVG would be right too.
I said choose the best answer.
Dang.
Also, a constant is right because a constant, 0 is a constant.
So 3 out of 4 answers are right.
What is the best? It's 0. So here we have a bridge. We apply a torque. What would happen if we apply the same torque? We're rotating about B. Would it rotate open slower or faster? Slower, why? Bigger distance, the I about the end is going to be less or greater than the I about the middle. So your I omega for the same moment times time, your I omega is going to, the omega is going to be smaller for the I larger. Something like that. Well, that's why. This is the wrong thing. No, that's why it doesn't work. What's the advantages of the variable thickness on the bridge? Oh, there we go.
What advantage is thickness?
Yeah, it's thinner here, thicker here.
Less or stronger than
Yeah, actually, yeah, the moment, this cantilever, so the moment is going to be the biggest in the middle, so therefore you need the biggest I. It also helps you out, that's really the reason, but for
Mass.
dynamics, when mass is closer to the center, and so
It's easier.
to rotate. But that's really not, the really, it's mechanics and materials is the real answer, but the dynamics, everything is their problem. There's lots of things going on here. Sharpie, coming back again. Basically, we can figure out what the impulse is. Exerts when it hits a test specimen, right? Because it's force times, integral of force times time. But now we have an angular momentum. And so therefore, we're going to also get an angular force times time times distance. Will give you your angular impulse, and from that you can calculate what the force is. Here we have another thing. Thrust when the engine is fired. Why is this going to rotate? Why is our shuttle going to dive into this? Yeah, we have an offset, so we're going to have a moment. So the force is going to cause us to accelerate, and the force is also going to cause us to dip, and you can figure out what your omega is if you know how long your engine is going to be going. So linear momentum, we have before L is mass times velocity. We have those pretty yellow things. What does a pretty yellow mean?
Vector.
Vectors, which means we're sad. It's not like energy, which is a scalar. So now we have to keep track of directions. So what do we have? If we have the MV, and then basically if we can add up all of the MVs all over our body, then are basically, and they're going to be related to the omega, and so basically what we can get is our angular momentum, which is the moment, whatever, that the MV of a certain, take a certain point, has a certain mass, times its velocity, times the distance from the center of gravity. That's how much we're spinning around. That was your angular momentum before. And fortunately for us, it works out that it's this I about the center of gravity times omega. That is going to be your angular momentum, and that's separately from your linear momentum. So it separates out that your angular momentum is this, your linear momentum is this, and those two are both happening. So if we're purely translating, then what? Omega is equal to 0. And therefore, we only have linear momentum. We don't have any angular momentum. So therefore, it's just like chapter 13, 14, 15. So that's basically why it works. So hg is 0, L is equal to mass times velocity. If we're rotating about a fixed axis, then what do we have? These true always are true. And in our special case, since we're rotating about a fixed axis, we can say that we can have the angular momentum about the fixed axis. It's your moment, in quotes, the force, with your linear momentum being your force times your distance, plus ig omega, and that turns out to be I omega. So just like in terms of acceleration, when you integrate the acceleration, you actually get this equation. So general plane motion, you have your linear momentum is mass times vg, hg is equal to ig omega. Those two are always true. And then what do we have? Angular momentum about point A is ig omega plus mass vg times distance. So it's again your mass times velocity times your distance. Why is this a scalar equation? Well, what direction is this? It's perpendicular. So this is in the z direction, and so we can treat this like a scalar because in a planar motion this is always in the z direction, where these are vectors because they have an x component, a y component, a normal component, a tangential component, an r component, a theta component. Those are vectors. But angular momentum, again, is always in the z direction in planar motion. So impulse momentum. Basically, how do we know we're dealing with impulse momentum? We're given L's, which are mass and velocity, and then we're basically forces and time. So if you're given forces, times, and velocities, or moments times and velocities, next equation, moments times time, integral of the moment times time is your angular impulse, integral of force times time is your linear impulse. So the new equation here is your moment times time, and that's equal to ig omega 2. That's your angular impulse momentum. So we basically start out with initial mass times velocity and I omega. We add a whole bunch of other stuff to it, external forces, and they don't have to be passing through the center of gravity. So these external forces could have moments about the center of gravity, and that's equal to your final angular momentum. So xy plane, linear impulse momentum, we can use the xy, we can use normal tangential, z direction, angular momentum, and so we basically end up with 3 scalar equations. So we begin x, y, z, internal reference frame, impulse momentum, oops, there we go, impulse momentum diagrams, ig if necessary, equations of motion, impulse momentum, 1 vector, 2 scalar, to get the, so you basically, 1 vector, 1 scalar to get the 3 scalar. And then if you have more than unknowns, then you basically need to go to your kinematics. So, what happened? We're going to do an example. Is there an example or no? After this. Okay. So, let's see if we have a general concept. Slab is rotating about its center of mass, G. How does its angular momentum about an arbitrary point compare to the angular momentum computed about G? What is its angular momentum about point P? How is that going to compare? Look at the equation for momentum about an arbitrary point P, and that probably will help you. Here they call the arbitrary point A. So how does HA compare to HG in this case? to our equation. HA is equal to IG omega plus MVG times D, right?
Yeah.
So the difference between the two is MVG times D. 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 MVG times C. What's VG? Right, we're rotating about here. VG is 0. What's D?
0.
Now D is this distance here, but VG is 0, and so 0, and so C is the right answer. Did anybody get the right answer? No. Normally it's larger than, but in this case, since we're what is the linear momentum of the slab in question 1? Best answer.
Best answer?
Yeah.
That gave that away.
And a constant omega. That's interesting. All right. 5, 4, 3, 2, 1. All right, when I say best answer, the answer should usually be
One of the
0.
two that are common.
Again, the linear momentum is mass times velocity in the center of gravity, which is fixed, so this is also 0.
There is just no velocity. You said it's 0 because there's no velocity, right?
Yeah, it's 0 because there's no velocity. The set is pinned at its center of gravity,
Okay.
so therefore
Not translated.
it's not translated.
So on number 1, you said it's same because when you do it about an arbitrary point, it's like having a fixed point at P?
No, it's
Or is that
HA is
same?
equal to IG times omega plus MVG times C. That was the equation.
So it doesn't even rotate about P.
So it doesn't rotate about P, but we can still calculate it,
The momentum at
the momentum
At P.
at P.
but there's no V.
And there's no, so but since the velocity of center of gravity here is 0, then this extra point, that is 0. And
I
so
was asking if it's rotating.
we're not rotating about point P, but we can still calculate the angular momentum. Similar, so this is an example here. We basically have an external moment, and we're out of time. It looks like, here's an example. We have an external moment, radius of gyration, and we have a couple. What's going to happen to our wheel? It's going to rotate and translate. So we're going to basically be sliding right here. And as we apply the moment, which direction is our wheel going to go? It's going to go to the right. Which direction is friction going to go? Also to the right, because the friction is what's pushing you to go to the right.
Oh, because there's a torque.
We have an external torque, and so with the torque, this is the point we actually want to spin that way, so force goes this way. So, what we could do is take our, in this case, angular momentum is not conserved, but if we had, if this was a spinning wheel, so like walk the dog, yo-yo, so you have no external forces, this is spinning, then angular momentum would be conserved about this point here because all of the external forces pass through this point. So in that case, you want to calculate the angular momentum about point A because that will be conserved even though we're not actually rotating about this point. So that goes back to your other question. We'll work on this problem.
Yeah, I already did the one.
Yeah, I know.
Yeah, Friday.
Yeah. Would you go to test, Mike?